The next topic is scattering or S matrix representation of multi-port network. Here we are not considering two port, we are referring for multi-port network. So that is your next topic is scattering or S matrix representation of multi-port network. Okay, we have seen what is S matrix or S parameters refers to. Okay, in a reciprocal network, okay, the junction media are characterized by a scalar electrical parameters, normally the absolute permeability and absolute permittivity. That what we have discussed in the previous section. That is your symmetrical Z and Y parameters. Okay, so the amplitudes are normalized in such a way that the square of any of these variables gives you the average power in that wave that is, so to define this we are considering the reciprocal network. So in the reciprocal network, the junction media, so junction media is nothing but where you are connecting your network. So the junction media are characterized by a scalar electrical parameters, namely absolute permeability and absolute permittivity. So the amplitudes are normalized in such a way that the square of these variables gives you the average power in that wave. Okay, why we are taking here the amplitudes? Because your S parameter defines the reflected wave amplitude and the incident wave amplitude. Okay, for an incident wave, let me take total power P. For the nth port, we can write, this is for incident. Okay, for incident wave power at nth port, it is Pin will be equal to half into magnitude of En square. Okay, for the reflected power at nth port, you can give Prn. This is reflected for the nth port half into Bn whole square. This is amplitude of the incident wave. Bn represents, this we have seen in the previous class. N is amplitude of incident wave and Bn is amplitude of reflected wave. So we can write the total voltage. Say you take V1 will be equal to Vi1 plus Vr1. This is the previous case I have shown. No? Total voltage Vn is equal to Vn plus Vn minus. This refers to incident and this refers to reflected. Same here I am taking V1. V1 is for the port 1. Okay. So then V2 for port 2, the total voltage will be equal to Vi2 plus Vr2. Okay, this is how for V1 at input port, this is at port input output port, this is input port and this is output port. I can write the voltages as V1 is equal to Vi1 plus Vr1. This is Vi2 plus Vr2. Okay, so in a two port network, we can write the normalized wave, or we can express the normalized wave as A1 is equal to Vi1 divided by root of Z0, which is equal to, what is Vi1 here? It is V1 minus Vr1 divided by root of Z0. Okay, similarly A2 is equal to, it is Vi2 divided by root of Z0, which is equal to V2 minus Vr2 divided by root of Z0. This is for the incident wave. For coming for the reflected wave, so normalized reflected wave, this is normalized incident wave. You consider normalized reflected wave, we can write V1 is equal to Vr1 divided by root of Z0, which will be equal to V1 minus Vi1 divided by root of Z0. It's coming to B2, which will be equal to Vr2 divided by Z0, which is equal to V2 minus Vi2 divided by root of Z0. So this you know, no? In last class I've shown how it comes as parameter. This is how you'll take two port. Here you have E1, it is B1. This is A2 and this is B2. Here it comes V1 and this is V2. This is, for this we had written this one parameter. Here you have the incident wave E1 and E2. B1 and B2 corresponds to amplitude of your reflected wave. So this is how you will be writing normalized incident wave and normalized reflected wave. Now we'll write what is a total power or net power flow into any port, it is any port is given by P is equal to Pi minus Pr, which is equal to half into magnitude of A square minus magnitude of B square. Like this we'll be getting the total power or net power flow into any port is given by P is equal to Pi minus Pr. This is equal to half into magnitude of A square minus magnitude of B square. Okay, this is regarding the total power into any port. In the normalization process, the characteristic impedance is normalized to unity. That is, your Z0 is normalized to unity. Okay, for two-port network, the relationship between the incident and the reflected wave are given by using scattering parameters. Now we'll see how this incident and the reflected wave are given by scattering parameters. Said no, it is in the normalization process. Characteristic impedance is normalized to unity. Okay, so again, the relationship between your incident and reflected wave are given by using S parameters. That is, B1 is equal to S11 into A1 plus S12 into A2, and B2 is equal to S21 into A1 plus S22 into A2. These are very important. That is, this also we had discussed in the previous class. The equation represents the S parameters. Now we'll see the physical significance of the S parameters. The physical significance of S parameters. That is, S11 is equal to B1 divided by A1 when A2 is equal to 0. Okay, we are defining the S parameters here. So S22 is equal to, it is B2 divided by A1. Sorry, S22 is equal to B2 divided by A2 when it is when A1 is equal to 0. Next you have S12 will be equal to B1 divided by A2 when A1 is equal to 0. S21 is equal to B2 divided by A1 when A2 is equal to 0. So, and what these S11, S22, S12 represents is S11 is your reflection coefficient at port 1. This is reflection coefficient at port 1 when port 2 is terminated with a matched line. Matched line here is nothing but you are matching the impedance. Okay, next you have S22 is reflection coefficient at port 2 when port 1 is terminated with a matched line. Next, S12 is your attenuation of the wave traveling from port 2 to port 1. S21 is attenuation of the wave traveling from port 1 to port 2. This is what your S matrix or S parameters represent. Either it will be reflection coefficient or it will be an attenuation of the wave. So S11 represents the reflection coefficient at port 1 when the port 2 is terminated with a matched line. This is reflection coefficient at port 2 when port 1 is terminated with a matched line. Okay, this represents the attenuation. S12 and S21 represents the attenuation for the wave traveling from which port to which port, that is given. So in general, what how we can write, we'll see for n port. Since the incident and the reflected waves have the amplitude and the phase, the S parameters are complex numbers for a multi-port network or components. So the S parameters are having both magnitude and phase. Okay, so the S parameters equation are expressed by B1 is equal to S11 into A1 plus S12 into A2 plus S13 into A3. So this can be extended up to S1n S1n multiplied by SAN. Okay, same way you can write for B2 is equal to S21 into A1 plus S22 into A2, S23 into A3. It goes on up to S2n multiplied by AN. So this you can extend up to n ports. So this will becomes Bn, which is multiplied by, which will be equal to Sn1 into A1 plus Sn2 into A2, Sn3 into A3 up to Snn. This also you can extend. This is how you will represent S parameters in the form of equation. This is nothing but your S parameter equation representation for multi-port network. Next we'll see the power losses. What are the different power losses in microwave networks? Okay. In a microwave devices or circuits, it is important to express several losses in terms of S parameters when the ports are matched, terminated. When the ports, you are having two ports, no, input port and output port. When the ports are matched and terminated, so it is very important to express the power losses in terms of S parameters. In a two-port network, if power fed at port 1 is taken as Pi That is your incident power. Next, power reflected power reflected at the same port is PR. Third one, and output power at port 2 is, and the output power at port 2 is P naught. Then we have the losses which are defined in terms of S parameters. What are the different types of power losses you are having is reflection loss, insertion loss, transmission loss, and return loss. So coming to insertion loss. In dB, how you can write it is 10 log Pi divided by P naught. Pi is your incident power, that is at port 1, to output power. The ratio of incident power to output power will gives you the insertion loss. Okay, the same thing you can write it as 10 log A square divided by, this is A1 square divided by B2 square. A1 is incident, the amplitude, incident wave at port 1. This is reflected wave at port 2. So this will be equal to 20 log 1 over S21. We are writing insertion loss in terms of S parameters. This is because S21 is equal to B2 divided by A1. We know this, right? S21 is equal to B2 divided by A1. This is insertion loss in dB. Okay. Next we have attenuation loss, or it is transmission loss. In dB, which will be equal to 10 log Pi minus Pr divided by P naught. Incident power minus reflected power divided by output power, which is given by 10 log 1 minus S11 square divided by S12 square. Here you can make the substitution for Pi, Pr, P naught in terms of A and B, and then simplify, you'll be getting this one. So I'm writing it directly. So attenuation loss in dB can be written as 10 log 1 minus S11 square divided by S12 square. Next you have reflection loss in dB, which will be equal to 10 log Pi divided by Pi minus Pr. So this will be equal to 10 log, it is 1 divided by 1 minus S11 square. And again you have return loss in dB. This is equal to 10 log Pi divided by Pr. This is equal to 10 log a1 square divided by b1 square, which will be given as 20 log 1 divided by s11 square. So this is how we will represent power losses in microwave network. That is, we are considering here is two-port network, two-port microwave network. Okay, so in the next class we'll see how you can represent S parameters for multi-port network. Okay, the next class we'll see how exactly we can represent the S matrix for a multi-port network, and we'll define each and every parameter of your S matrix. Okay, that will continue in the next class.